Hello, calculus fans. Today we begin chapter 9, and we talk some about sequences and series. A lot of folks have an idea of what a sequence is, but the main definition is a little bit more sophisticated than what you might suspect. So the formal definition of a sequence is a function, and its domain are the positive integers, and the range is reals. So suppose we talk about this function being a, and typical function notation is a of 1. When we're talking about a sequence, we write it very specially as a sub 1. And so a finite sequence is written as a sub 1, a sub 2, up to a sub n. And an infinite sequence obviously would look like a sub 1, a sub 2, a sub n, and so on. So if we look at what I've put on the screen, these are all finite sequences. This is an arithmetic sequence, which means you get the next term by just adding the same thing to the previous term. The first term is 1, and what we're adding, sometimes called the common difference, is 2. This is a geometric sequence, and each term is obtained from the previous term by multiplying by a fixed number, sometimes called the common ratio. And I'm sure that you've seen this stuff before. So the first term here is 64, and the common ratio in this case is a half. The next one is more interesting, and you probably have seen this too. This is the Fibonacci sequence. And we define this recursively, which means we get the next term from previous terms. So the way that this is defined is the first term is 1, the second term is 1, and from then on, as long as n is greater than or equal to 3, a sub n is equal to the sum of the two previous terms. So that's the idea of what we call a recursive definition. And we will, I think, when we get into chapter 10, look at how we can get an explicit definition for the Fibonacci sequence. In other words, figure out what a sub n is just based upon n. But you'll see that that's pretty challenging and pretty ugly. Okay, let's move on to some examples now. So, an infinite sequence, obviously, is a sequence that never ends. We talk about the limit of such a sequence as n goes to infinity equaling L if that limit does exist. So just for an example, suppose we have this is notation, suppose we have a sequence written as 3n minus 5 over 2n. And we want to ask the question, does this have a limit as n goes to infinity, and if so, what is it? So this should remind you of the work that you did with rational functions, but the way that we can analyze this is to multiply top and bottom by 1 over n, and we get this. And now if n goes to infinity, this goes to 0, and we see that this is just equal to 3 over 2. Okay? So I think you've seen most of this before, but what you notice here is, once again, are the properties of limits. And you should just take a look at those. What's really nice is everything that you think is true is true. So the product of the limit of a product is the product of the limit. The limit of a quotient is the quotient of the limits. And that's a lot easier than, as you remember, what we were dealing with when we were looking at derivatives. Okay, so let's keep going. Okay, so let's just take a look at this pattern here. If we have an arithmetic sequence, first term a sub 1, and each successive term is obtained by adding d. Now look, this is the second term. See that number? This is the third term. See that number? So hopefully that helps you see that the formula for the nth term is going to be the first term plus n minus 1 d's. And similarly with a geometric sequence, the pattern is the same. And so the nth term is just equal to the first term times r to the n minus 1. So pretty simple just by observation. Well, I'm sure you've heard of series as well, and a series is defined to be just the sum of the terms of a sequence. So whereas a sequence is a function, a series is simply a number. And there are some formulas for these that you should expect to remember and probably have seen. I won't prove them for you, but they're easily proven. So the formula for the sum of an arithmetic sequence is n times a sub 1 plus a sub n over 2. And the formula for the sum of the first n terms of a geometric series is a sub 1 times 1 minus r to the n over 1 minus r. All right, so those formulas I am sure you have seen going back as far as Algebra 2 at least. So we can consider an infinite sequence, and similarly we can consider an infinite series. Now you should understand that the only way that an arithmetic series, an infinite arithmetic series will ever converge if it's just this. Anything else will diverge. But a geometric series is a lot different. Remember the sum of a finite, k goes from 1 to n, that's going to be a sub 1 times 1 minus r to the n over 1 minus r. Now this might converge. An infinite will converge as long as r is less than 1. In that case, absolute value of r less than 1. In that case, we write this, and if the absolute value of r is less than 1, this term will go to 0, only if the absolute value of r is less than 1, and then all we're left with is a sub 1 over 1 minus r. So a quick example would be 64 plus 32 plus 16, and so on. An infinite geometric series will converge to the first term divided by 1 minus, in this case, a half. And that turns out to be 128. It's kind of amazing that an infinite sum can converge. But you've seen so many wonderful things with the idea of infinite up to this point that nothing should surprise you anymore. So that concludes this little bit on series and sequences, and I'll see you next time where we get into some real calculus.